Welcome back. So we've got this new formula, enthalpy equals N delta H, and let's see how this thing actually works in practice. These first questions are really straightforward uses of it. They say the molar enthalpy of combustion for methane is 890.5 kilojoules per mole. This means every time you burn a mole of methane, 890.5 kilojoules of heat is released. We know it's released because the number is negative. So the question would be, how many moles of methane are we talking about here? Our formula says, I can tell you the total heat that's released if you give me the number of moles of methane and the molar enthalpy of combustion for methane. This is the 890.5, the number of moles we need before we can go on. So how do we get a number of moles? Mass divided by molar mass. The mass is 529.0 grams. And methane is CH4, so its molar mass is 1605 grams per mole. Hit pause and work that out if you aren't sure where it came from. You definitely want to be able to do those yourself. And 529 divided by 1605 is 32.9595 moles of methane. So, total enthalpy will be our number of moles, 32.9595 moles of CH4, times our delta H is 890, that doesn't even vaguely resemble a 9, 890.5 kilojoules per mole of CH4. And now you say, hang on a second, Faye. Why is there a CH4 here? That wasn't mentioned up top. They said it's the molar enthalpy of combustion for methane. When they say that, they're saying when we talk about moles in a second, we mean moles of methane. Second thing, where did the negative go? Generally, when I'm doing this calculation, I don't bother including it. At the very end, if they ask me if energy is absorbed or released, then I'll go back up here and check. But for this math, I tend to drop it. If you want to carry it, fair enough, you'll get a negative E, and there's nothing wrong with that. So we multiply these two things together, and 890.5, I get 29350.4 kilojoules. And for significant digits, the mass had 4, our delta H had 4, the molar mass even had 4, so we get to trim this down to 4 sigdigs. Sadly, we can't write 29,350 using only 4 sigdigs, so the options are, you can go to scientific notation and say 2.935 times 10 to the 4 kilojoules, or shift it to megajoules, divide by 1,000, and you will get 29.35 megajoules. And when they say how much heat is produced, as in released, when the question already says that, you kind of aren't obligated to include the negative sign in your answer, but if you put it in, you're a diligent student, good for you. If the question is ever like, what is the enthalpy change, and they don't say anything about whether it's absorbed or released, then you should definitely include either an English word like absorbed or released, or you should include the sign. But in a question where we act like we already know that it's being produced, then this is a nice to have, but not a must have. Fair enough? I think in the questions we give you on exams and assignments, we're pretty clear about our expectations on that, so don't worry, we're not going to try to get you with it. If the molar enthalpy of combustion for propane is this, so we have our delta H is 2219.9 kilojoules per mole. Don't just say moles, say moles of propane. When the questions get more complicated, you'll be glad you do this. What mass of propane would have to be burned to generate? Okay, so this time they're saying we want the total energy that comes out of here to be 23.95 megajoules. And the question is, how much propane is that going to take? So same formula, but we're using it in a different way. Total enthalpy is 23.4 megajoules. Number of moles is to be determined, and delta H is given. Now, I want to put these numbers into the formula and solve for n, but there's a small problem. Our units don't match currently. One of these things is in kilojoules, the other is in megajoules. I'm going to take this mega and multiply it by 1,000 to get 23,400 kilojoules. And now we're good to go. Both of these are speaking kilojoule, and that's all right. If you want to turn this into megajoules per mole, go ahead. You'll get the same answer as us, but your work in the middle will just look a little different. So 23,400 kilojoules equals an n I don't know times 2,219.9 kilojoules per mole of C3H8. Hang on a minute, you say. Where did the negative go? Like I said before, I often leave out the negatives when I'm doing this. The other alternative is you could make this negative as well. You don't want your number of moles to come out negative. That doesn't make a great deal of sense. So either make them both positive like I did, or make them both negative if you're a little more rigorous, and either way you'll get the right number of moles. So our n is 23,400 divided by 2219.9. I get 10.541 moles of methane. I'm sorry, propane. And if they said how much propane, we'd be done, but they said what mass of propane, so this isn't going to cut it. We need one more step. The mass of something is its number of moles times its molar mass. Our number of moles is 10.541. Molar mass for propane is 2403, 3211. No, I'm sorry. 3 carbons, so 3603 plus 808 is 4411. That's a number I've heard before. Okay, so 10.541 times 44.11 gives 464.964 grams. And how are we doing on sig digs? Molar mass had 4, delta H had 5. This enthalpy that we produce only has 3 significant digits, so we have to trim this answer down to 3. And so we keep 464, round up. It'll be 465 grams for our finished answer.